Okay, so in experiment 8, we're using a setup like this. And I should have taken a picture of the little spectroscopes, although they're not much to look at. There's little boxes that are black plastic. They have a grating in them. There's a slit here. We aim the slit at a light source, and here these are tubes of elemental gases like hydrogen or mercury vapor. And those are going to be excited using electricity, and then they're going to give off light, and that's from the electrons being excited to higher energy levels and then transitioning back down. So the light from that is going to come through here, bounce off a transmission grating, and then hit a measurement scale over here. Now on the one that we're looking at, this is reversed and the measurement scale is on the left. You just tip it over, but I thought it would be nice to have the numbers right side up. So we're looking at how the light gets separated according to different wavelengths. So this is what an emission spectrum for the element krypton looks like. And we see that there's a lot of lines, right? They're thin lines, and each line represents a single transmission or transition from one energy level to another for an electron. What we would actually see in these spectroscopes, and the reason we're using them is because they're inexpensive and we can have enough that each student gets their own and gets to look through it themselves. So this purple here is a combination of all of those lines. It's just not resolved because they're so close together. And then here we see some green. From looking at this, we see it's actually two lines. The yellow here is appearing as one line, and then we're only seeing very faintly the orange and green, the arrow's green, the orange and red lines here. Now the scale here is backwards because of how the transmission grating works, and so this is 4 going to 7 to the left, not the way we usually read things. This corresponds here to about 450 nanometers, and we see on this scale there's 400 and 500, and 450 nanometers is right here. This, being a very inexpensive piece of equipment, is not going to be very accurate. It's going to be off, and we see that here, that this seems to be centered on the 450, and here it ends at 450. And so what we're going to do is we're going to calibrate the particular spectroscope that we're using. And we're going to do that by looking at Mercury spectrum and reading the lines in the Mercury spectrum. And so here's the Mercury spectrum. This is what's being called the orange line. That's green. This, I'm pretty sure, is background. This is the blue line, and this one over here is the violet line. Not super obvious. We're going to identify where they are on the scale for this spectroscope as best we can. Obviously, we're not going to be super precise like in the example. So let's just take this one right here. So there's 450. This is 400, so this line's 410, that line is 420, and so we're just going to do the best we can, thinking, well, maybe it's a little bit above 410, I don't know, maybe call it 412, but if you called it 410, that would be fine as well. So we're going to record that as the measured wavelength for that purple line. From the example here, there's the violet line. Here's the known wavelength. So we know from measuring these with precise instruments that the violet line for Mercury is at 404.7 nanometers. Now, in this example, this person must have had a better spectroscope with better resolution, because they're saying it's 409.2. And honestly, I think the best we could do on ours is 412 or something like that. So you're going to make a measurement here, and it's supposed to correspond with a known measurement here. And then you're going to graph the data here. So the known wavelength is on the x-axis, and the measured wavelength is going to be on the y-axis. And what will happen is we'll get hopefully a line. It's maybe not going to be as beautiful as that, but it's going to be a line. The slope will be close to 1. We should see a positive slope, and there's some intercept here. But the equation for the trend line is going to give us a way to correct the lines that we observe to see, well, my spectroscope's a little off. I need to correct it and see what is this really telling me. Does that make any sense?
Yeah, that makes sense.
Okay. So that's all about calibrating the spectroscope. Then you're going to look at the hydrogen spectrum. And so there's 3 lines in hydrogen. There's the red one over here, and this one is, people call them different colors, but that looks like cyan to me. You might call it blue, and then there's a violet line right here. And so we're going to read these off of the scale and the spectroscope as best we can and write those down. And then we're going to plug those numbers in for y in the equation for the line and solve for x. And the x value will be the corrected wavelength, which hopefully will be closer to the expected or known wavelength for hydrogen. And then it's also going to ask you to do that for 2 of the other 3 substances here. There's air, which is a mixture of gases, nitrogen, and neon. And of course, these guys are a big mess, right? So how do you do all of these lines for nitrogen? Better pointer. Well, you don't. You just measure a range. And so you might say, well, it looks like it's stopping here and it goes to about there. And so record a range for the red. You might say, well, I think that's about 615 to 680. And record the range. And record a range for the yellow and for the green. For the blue, if you're feeling ambitious, you could, you've got a range here, and then there's a gap, and there's another thing over here. And then you've got the purple down here. Minimum, I want you to record 4 things. So you don't feel like you have to do all the colors. And then to correct those, let's see. So I think I said it looked like 610 to, 685. When we correct that, how do we do that? Well, you're going to take the 610 and plug that into the equation and get a corrected value. And then you're going to take the 685 and plug that into the equation and get another corrected value. And you're going to report the range in the corrected box. Does that make sense?
Yep.
Okay. So the other part of the experiment is, let's see, it's up here, has to do with the Rydberg equation. The Rydberg constant is this R with a subscript H. And that is a constant that allows us to relate the energy difference between 2 levels, 2 principal quantum numbers in a hydrogen atom. And it doesn't really have a physical significance. It's just an empirical number. The other things we have in here are Planck's constant, H, and C, which is the speed of light. So what we're measuring is not the energy, we're measuring the wavelength of these different transitions. The wavelength is related to the energy, though, through this equation. Energy is equal to hc over lambda. So we can put these two together to make something that's a little more useful. So if I say that delta E is equal to hc over lambda, and delta E is equal to negative hc RH times the quantity 1 over nf squared minus 1 over ni squared. Simplifying this, I can look and see, well, I have an h on both sides, so I'm going to cross that out. And I have a c on both sides, so I'm going to cancel that out. And that's really all the simplifying we can do. And so I'm just going to clean this up a little bit. Let's move this over. So combining those two equations, where are they? Here they are. We can get this 1 over lambda is equal to negative Rydberg constant times 1 over nf squared minus 1 over ni squared. Nf is the shell that the electron is falling to, the one it's going to, the final one. So this is going to be a smaller number. Ni is the initial shell, the one that is coming from. So that's going to be the higher number. And those are going to be integers like 1, 2, 3, 4, etc. This is the wavelength, and this is the Rydberg constant. Now we know what the Rydberg constant is, but just to kind of demonstrate it, we're going to use the wavelengths that we measured using our spectroscope and the hydrogen lamp and calculate the Rydberg constant and see how close we come. So the Rydberg constant has the unit of per meter, or meter to the minus 1. So what that means is the wavelength also needs to be in meters, not in nanometers. So what we're doing is we're plugging in the wavelength that we observe, converted to meters, and we're plugging in these two energy levels, and we're calculating R. Now, normally I'd say let's rearrange the equation and solve for R. Well, that gets kind of messy. It's actually easier to just look at it this way. You can plug the numbers in to both sides here and simplify those things and come up with a number for the Rydberg constant. The Rydberg constant is 1.097 times 10 to the 7th. And the data here is not going to give us perfectly the Rydberg constant, but it's going to give us very close. So if you're off by more than a factor of 100, your calculation is to blame. It's not the data. How do we know what N and F, NF and NI are? Actually, for that, we need to look at the report sheet. So here's where we'll record the Mercury wavelengths. What color you call them, use a color name that makes sense to you. The measured wavelength, the known wavelength. These are in the table in the pre-lab part. Here's where we put the equation for the line and the R squared value, and don't forget to include the graph in your report. Then you're going to do hydrogen and, here's for the other two lamps. So for the hydrogen lamp, I want you to show me how you calculated the corrected wavelength for the red line. So you're going to take your red line measured wavelength, you're going to plug it into the equation that you get from your graph, and you're going to solve for x. So that's what's happening here. Calculating Rydberg's constant. So the red line is for an electron going from n equals 3 to n equals 2. So they're telling us what Ni and Nf is. So Ni is 3, and NF is 2. Solve for the Rydberg constant. So we've got that equation, 1 over lambda. And so here you're going to take your corrected red wavelength and convert it to meters. Put that in there. And that's going to equal negative RH times 1 over the final squared, 2, minus 1 over the initial squared, which is 3. Don't worry about taking these fractions and simplifying them and subtracting them and getting common denominators. This isn't math class. Just do it on your calculator. Just do 1 over 4. 1 divided by 4 minus 1 divided by 9 equals, and get this value. And then you're going to take 1 over your wavelength, and you'll divide by the value you get here and change the sign. And you should end up with a value that's very close to the known true value for the Rydberg constant. So you'll write those in for violet, the blue-green, and the red, average them together, calculate the percent error, the same way we've done before. So here's our accepted value. You're going to use the average as your experimental and calculate the percent error.
Real quick,
yes.
Why are we using the negative sign in the equation?
The negative sign is in there because when we're talking about, it's an excellent question. We have positive and negative energy, right? So this is the energy for the electron. The electron is going from a state of higher energy to a state of lower energy. And so the change in energy is going to be negative compared to the energy of the photon, which the energy of a photon has to be positive. So this, keep using the wrong pointer. The negative here is so that the signs match up, basically. Because the photon is positive energy, the energy calculated for the electron is going to be negative, and so the negative sign just takes care of that. It's a little bit like the Q reaction equals negative Q solvent or solution in calorimetry. It's the same energy, but one thing's getting it, one thing's losing it. Does that help?
So it's because the final is a lower energy state than the initial?
Right.
So you're going to get a negative number there, so you have to put the negative. So
so this quantity here is always going to be negative. And so when we combine the negative here with the negative here, we get a positive for the change in energy because it's the change in energy for the photon, not for the electron. If we go from a lower energy to a higher energy, then this is going to be positive and this delta E would be negative, and that would imply that it's absorbing energy instead of releasing energy. But it's releasing energy. The energy released is the photon of light.
That makes sense. Thank you.
Okay. Does anybody else want to chime in with any questions about this?
I have a question.
Mm-hmm.
For where it says 7, on the instruction sheet, I got confused. Where it says you should enter known wavelengths on the y-axis and measure on the x, so it's opposite.
That's wrong. Thank you. Thank you for catching that. I need to fix that. Yeah.
Okay, so it's opposite, Mrs. K, because I have to redo my graph.
So the graph is correct.
Okay.
The graph is correct because what we do in science is the thing that we're measuring goes on the y-axis, and the thing that we're controlling or the thing that's known goes on the x-axis.
Okay.
The reason this is a little mixed up is that some instructors recognize that, well, these students, most of them aren't going to be scientists. They're not going to understand the subtlety of it matters which one is which. Let's do it the other way so that they're solving for y because it's easier. And I don't like that. So we want known on the x and measured on the y. Thank you very much for catching that.